So there's a few very simple things. I wrote an example. I don't think we'll actually do the example, but just things that you need to be able to do. So one thing is verify a differential equation. So this is a really important concept, and really among all the things you're asked to do, verifying is one of the simple ones because you don't have to solve. Verifying is much easier than solving. And when we say to verify something, it says, okay, we've already given you the answer. We just want you to make sure the answer is correct. So what do? Well, you plug the answer, that solution, into the equation, and you just make sure that the sides agree. So if we were to carry this example out, we have e to the 2x. You say, okay, well, what does that mean? Well, you'd plug e to the 2x here, the derivative of e to the 2x, which is 2e to the 2x, and the second derivative, which is 4e to the 2x, and then you work out and you say, does that equal 0? That's what you do. It's very straightforward. Now, why do we do this? Well, it makes sure that we found solutions. It can actually be used to say, what are the right constants to pick? So for example, when you're doing undetermined coefficients, what you're really doing is you're running through the verification process and saying, hey, how do you pick your constants? So this idea of plugging plugging functions into your differential equation actually shows up quite frequently. There's another important idea, which oftentimes we don't phrase it using the word superposition, but it shows up implicitly in many places, which says, hey, if you have some solutions to a nice, we'll call it linear, homogeneous differential equation, and I'm not going to do a lot of vocabulary. Homogeneous just means that you equal 0. So for example, this is where you equal 0. Then what you can do is you can combine solutions together. So if in this case, this is linear, it doesn't look very linear with all these x pieces, but the x pieces aren't what matters. It's not what determines whether it's linear or nonlinear. It's the parts with the derivative, and that is linear. So it's something y prime, something y double prime. So we can say, hey, I could, once these were verified, you could combine. So you can say, hey, ae to the 2x and be to the x squared are also solutions to that differential equation. So that's what superposition allows us to do. It says, hey, let's glue together solutions. We should also make sure we understand the general solution versus the particular solution. Some problems might say, find the general solution. In that case, we want those constants. Make sure you have the constants. And the number of constants should equal the number of derivatives involved. So if it's a first order differential equation, how many constants? 1. Second order should have 2. 17th order should be 17. Not on the test, because that's too hard. But okay. But we understand the philosophy. However many constants matches the order of the derivatives. So the general solution, make sure you throw the constants in. There's also the notion of particular solution. Now, particular solution just says, look, I only need one solution. Now, sometimes we mean find any one solution, which is perfectly fine. And that's one of the things we finished off with. One of the last topics was finding particular solutions to, for example, second order differential equation, method of undetermined coefficients, variation of parameters. We just said, just find one. Or you might have to say, I need to find a particular one, which leads us into initial value problems. And in that case, we say, look, we not only give you the differential equation, we're going to say what happens to the function at that point, the derivative of the function at that point, and maybe a few others, just depending upon what order we have. And then we say, all right, find the particular differential equation, which solves the differential equation and also matches the behavior at the point we want. In other words, we're basically saying solve for the constants. And when we do that, well, what happens? It usually leads to a system of n equations, n unknowns. 2 equations, 2 unknowns, our bread and butter. You should say, look, I can solve 2 equations, 2 unknowns. No problems. No problems. And if you can't, well, Maybe a small problem. But that's something you should be comfortable with. All right. These are some small basics. Any questions? Should we pause? Okay. So the next page, and by the way, this is in Canvas, so if you just want to download it from Canvas, this next page is perhaps the most important page. If you can do what's on this page, it's hard to get below a 50% on the test. If you can't do what's on this page, you're in trouble. Now you're probably thinking, that's a very packed page, Steve. Yes. But this is first order differential equations. There is a fairly substantial amount of first order differential equations on this exam. And so you should be comfortable with all the techniques. And I would say that, yes, let me just say, you should be comfortable with all the techniques that is listed here. So the reason we talk so much about first order differential equations is we actually have a lot of options. When we get to the second order, higher order, we don't have very many options. We kind of get stuck because there aren't very many good techniques. But here we have 4. So you want to make sure you're comfortable with all of them. So the first bullet point is separable. So separable differential equations are the ones that you can separate. That's the word sort of gives it away. Now usually that involves lots of things that are multiplying, because what you're going to do is you're going to move stuff around by dividing from one side to the other, maybe multiplying one side to the other, and you're trying to isolate the variables. So all the y's on one side, all the x's on the other side, or all the t's. Who knows what the variables are? And it just depends on the problem. And so that's the idea. If you can separate, it's separable. And then you're like, great. You really have 2 integral problems, one on each side. You integrate both sides. And then you uncomplicate. See, separate, integrate, uncomplicate. And that's just a fun way of saying solve for your function and or your constant. Now, I should mention that there's really sort of 2 notions of solutions, implicit versus explicit. So when we talk about implicit, it says you don't actually have to solve for y. You can have a really unpleasant expression involving both x and y, and that's okay. When we talk about explicit, that means, hey, you've got to get y by itself. And usually if we just say, solve for y, we're looking for an explicit answer. But sometimes we'll go out of our way to say, give us an implicit answer. And that can be actually a clue, because some techniques don't actually really work well with implicit. So for instance, linear is not built for implicit. And so if you see the word implicit, it's probably not linear. In fact, it's probably either exact or separable. It's one of those nice things to look for. Probably, who knows? Who knows what mysteries they've baked into the exam. So yeah, separable. Another thing is, keep in mind, they might write y prime, or they might write dy dx, or dy dt, whatever your variables are. Be comfortable jumping back and forth. So for separable, I really like the dy dx notation, because I like to separate the d's. So like dy on one side, dx to the other side. But sometimes they write dy dx and say, it's easier for me to think of it in terms of y prime. For example, in linear. I often think of linear in terms of y prime. So it's y prime plus something times y equals something. And we say, okay, so anything which can be written in this form is linear. It may not start in that form. And one thing to watch out for is make sure what's in front of the y prime is a 1. If it's not a 1, fix it. You divide through. So you say, all right, you start with that form, and then you find what's called the integrating factor. So the integrating factor is you grab that middle piece, you integrate it, and then you take e to that. And that's your row. Multiply both sides by that expression. The left-hand side becomes a derivative. By design, it has to happen. If it doesn't, mistakes were made. Check your work. And then you can integrate and you get your solution. So that's linear. There's exact. All right. So that's, ideally it looks like m dx plus n dy. But again, this might be something where they start with a y prime and say, look, we can write that. And for exact, you kind of pull this out when you have something where it says, these m and n, it looks hopeless, hopeless. All these pieces of y, all these pieces of x, how could it possibly work? And you're like, when it's hopeless, there's the most hope, because this is a beautiful problem. If it's exact, it works so well. The idea is essentially these are more or less two derivatives of the same function. One derivative with respect to x and one derivative with respect to y. So you say, okay, you integrate that part with respect to x, integrate this part with respect to y, and you say, there's my function, I just got to sort of combine them together. So to combine, you say, do they overlap in the right way? And if they do, perfect. You put their common overlap, and that should be parts that involve both x and y. You grab pieces which just have x, you grab pieces which just have y, you set it equal to a constant, life is good. So you should hope for exact. You should hope for it. It's one of the best kind. Now the last one is substitution. And I use the phrase manipulate. So manipulate just means just rewrite it. And oftentimes you can tell pretty quickly whether it's separable, linear, or exact. You know, things like, there's just a single y prime and a single y. All right, probably should think linear. There's lots of multiplication, separable. It looks terrible. Exact. So if none of those hold, and it might be that none of them hold right away, you look for substitutions. And there's more or less 3 substitutions you need to be able to carry out. And we tell you what they are. You need to do homogeneous. And usually we say this is the one where you say, think of u as y over x. So you write your function as y over x. So everything becomes a y over x. But I actually think it's easier to say, replace y by u times x. So if you look at the solutions, for example, to last spring, I go through and say, look, this is how it works out. How do you recognize homogeneous? Everything has the same degree. That's what it means. Same degree, homogeneous. Bernoulli, u equals y to the k. How do you recognize Bernoulli? Well, Bernoulli will look like y prime plus something of x, y equals something of x times y to some weird power. I won't figure out what the power is, but essentially if you have a weird power here, you're off. You know it's Bernoulli. And the way you proceed, you divide this over, y to that power, and that tells you whatever you see right there, that's your substitution. So Bernoulli is just saying u equals y to a power. Then the third one you should be able to do is if we give it to you. So we're like, hey, here's a substitution. Carry it out. Tell us what it is. So be able to do that. And there'll be an example of that on Wednesday, depending upon which time you come. So as I say, this is super important. Make sure you can do all of these. Are there any questions? Are you comfortable with first order? All right. Well, another favorite, of course. Everybody loves a good story problem, also known as a word problem. And more or less, you should say, look, you should anticipate that there should be a problem like this, at least one like this. And they more or less fall into 3 categories. So these are the 3 categories of applications we've talked about, and they're the ones that are most conducive to word problems or story problems, if you will. So be ready to do these. So the first one on the list is population. Now, we might just give you a differential equation for population, but if we don't, then we're going to tell you it's one of two things. Exponential, which is really not interesting, but for some reason they've put it on old exams. Who knows, it might show up again. And that's just p prime equals kp. It says population behaves like the exponential function. Or logistic. And this one they've put on old exams. Well, it's a little bit more interesting. P prime equals kp times m minus p. Now, here logistic is more interesting because the solution is certainly more interesting. And the solution is on the equation sheet. So that's good to know. It's also important to know, for example, what things represent. So k, in some sense, in the exponential model, represents something slightly different than it does in the logistic model. So k says, in the exponential model, what proportion of the population am I growing by? But it's more subtle, because it depends not just on your current population, but sort of like how much room do you have left to grow. So if you think of m minus p, that says, well, how much growing room do I have? So it's slightly different. But m, you should recognize. M is, you can think of it as carrying capacity. How much can the environment support? Well, then it's also the long-term behavior. What happens in the long run? So, yeah. So anyways, what do we test on? Well, usually we test on, can you figure out what m is given some context? Can you figure out what k is given some context? Can you use it then to solve? We might say, if m is this and k is that, how long until the population reaches 400 or something? Those are the types of questions that we might use. And really, a lot of it comes down to understanding. The second type of problem you might see is mixing problems. And usually it's phrased as some compound mixing in a tank. Usually we do salt and water because that seems fairly harmless. So what does it mean, mixing problems? Well, let's just phrase it in terms of salt, so I'm using S. Say, well, the way that salt is changing, there's salt coming in, and there's salt going out. And you say, well, what's the rate it's coming in? And subtract the rate it's going out. And that's the setup. And you're like, all right, well, that's great. How hard could that be? Well, hard enough that we put it on a test. And so there's a couple of things. I like to draw pictures. So you don't have to be a very good artist. Like, look, we can all draw that. That's not a hard picture. And you just draw a little thing going in, draw a little thing going out. Now, how do you set it up? Because I want to be very explicit here, because I know people have had a hard time setting things up. Well, if I set up my S prime, you should think of it as there's some pieces. And is that enough pieces? I don't know. Maybe. All right. What's in the box? Well, read Steve's mind. So if you're one of those people who has a hard time with mixing problems, we're just going to run through it really quickly. So you'll have a concentration of what's coming in, and then you have a rate of what's coming in. So to give it a very explicit example, suppose you have 3 gallons per minute, and there's 5 pounds per gallon. Which one of these is the concentration?
5 pounds per gallon.
Yeah, the 5. Which one's the rate coming in? The 3. So 5 times 3 is 15. That's your inflow. And you're like, great, you're halfway there. Then you have, down here, you have a rate going out. And here, this is the fun one. This is the amount in the tank at time t. So you might say, okay, well, let's say there's 1 gallon per minute going out. And so, where does the 1 show up? Well, it shows up there. How do you figure this out? Well, there's not quite enough information, because what's happening? If you have 3 gallons in and 1 gallon out, what's going to be happening to the fluid? It's increasing. So what you have is you say, oh, with every moment of time, it's going to be rising. So your water level is going to be going up. So you take the initial amount, let's say there's, at t equals 0, there's 50 gallons. Then what you'd say is like, oh, well, there's the initial amount plus you look at the difference times t. So those are the slots. There's basically just 4 slots. And if you understand how to fill them in, you can set up your differential equation, and life is good. And so mixing basically leads to linear first order. So this is a great way to put linear first order problems on an exam. And we like linear first order problems. All right. Any questions about mixing? All right, we're well mixed. Okay, good. Springs are the last story problem. I know we haven't gone to many second order problems, but mx double prime cx prime plus kx equals f of t. Now f of t is your external force. It's almost always 0. So don't worry too much about this. You should think of this as 0. So you have your pieces. M is your mass, c is your damping constant, k is your spring constant. Now sometimes they might not give you k directly. They'll do something mysterious like say, if you put a force of 5 pounds, it's stretched by 2 feet. And you say, well, wait, what does that mean? Well, they're really trying to have you use Hooke's law. You say, oh, force is 5, x is 2, so k is 5/2. That's if they're mean. I'm not mean. But I don't write all the problems, so maybe somebody is mean who wrote that problem. Maybe there's not a spring problem. Who knows? I know. You'll know soon, too. Come Thursday, we'll all know. So essentially, these are not bad. Once you set it up, it's pretty straightforward. This is a second order constant coefficient. And you're like, great. Life is good. We love this. So where does the story problem come into here? Well, oftentimes it's a matter of solving it, setting up the motion. But you also need to be able to categorize things like undamped, underdamped, critically damped, overdamped. So you have to know, what does that mean? What's the behavior? And we do like to pick, I will say, very much on critically damped. It shows up in a lot of word problems with springs. In some sense, it's a really good setting if you have a mass spring dashpot or mass spring damper system. But the reason we like to pick on it is because it really says that's the one where there's sort of a unique setting for your damper and trying to find it. And so it all comes down to understanding the roots of the polynomial that's associated with this differential equation. So say, hey, great, turn it into an algebra problem, solve the algebra problem, and life is good. All right, well, okay, your 3 possible categories of word problems, and none of them are too bad. I think the hardest one to set up can be mixing. There's a lot of words that go into that, but usually just sort of say, look, just start reading it, have a picture, start labeling things, and it's not so bad. All right. Again, are there any questions? Okay, good. We're making great time. I predict we'll finish with time to spare. So that brings us to one of our favorite differential equation problems, because it's one where we don't have to solve the differential equation. We always like differential equations where we don't have to solve them. And this is, the fancy name is the autonomous differential equation, but it's really differential equations where it says y prime equals f of y. And we're trying to say, what are the critical points? Well, the critical points are where f of y equals 0. So really it comes down to saying, hey, when does something equal 0? and finding those values. And so, all right, great. Now the reason we care about these as far as the differential equation goes, these correspond with constant solutions. So those are oftentimes very interesting things. Now, you want to be able to do a couple of things. You want to be able to identify it, where the critical points are. All right, set f of y equals 0, solve, great. Usually algebra, that's not so bad. And then you say, all right, phase diagram. So the goal of phase diagram is you draw a line, and you say, all right, on my line, I'm going to mark my critical points. So you go through and you mark them. The only thing that matters is you get an order. Don't worry about the spacing. All right, maybe we have that many critical points. We have 4. And, we'll label it. So there's maybe, I don't know, I'm just making numbers up here. I'm good at making up numbers. So let's say those are our critical points. All right. Well, what you do then is you sort of put on your first derivative test from Calc 1. Say, what's happening to the first derivative? Because really that's what y prime is. It's the first derivative. You're trying to say, what's the behavior? And so what you do is you test every single interval, because the critical points are where behavior could change. Now, it doesn't have to. So that's why you have to test every single one. Does it matter which point in between you pick? So if I'm between -5 and -1, it doesn't matter which point I pick. Do I have to pick -2? No. I could have picked -π. But what should you pick? Easy numbers, yeah. So remember, make life easy on yourself. I mean, we love ourselves. We're like, oh, we're having a hard test. Let's just pick easy numbers. Life will be good. Okay, so we'll go through, and again, since we don't actually have a function, we'll just make up some numbers here. All right, so we have the signs. Now, what you really should be thinking about is the signs indicate direction. So, negative says, which way do we move, left or right? Left. So wherever you see a negative, you put a little arrow to the left. Lots of negatives. Positive means what? To the right. To the right, to the right. When the derivative is positive, we move to the right. Okay. And then you say, well, what kind of points can you have? And there's 3 kinds. There's stable points. And so 3 is an example of something which is stable. And that's just things move in. Follow the arrows. Things are pointing in. There's also, of course, unstable if things move out. So the arrows point in the sort of moving away in both sides. And then the last thing is you could have things which are semi-stable. Which means like on one side it approaches, but on the other side it moves away. So those are the possible categories. So make sure you know how to classify. So in particular, if you have a question like this, there's 3 main things. Know how to find the critical points, know how to make this diagram, know how to identify stable, unstable, semi-stable. Now, one thing they might ask, and they have in the past, is they say, well, suppose I tell you where you start. Can you tell me where I end? So, suppose I tell you that at time 0, I'm 0. Can you tell me where I'm going to go in the long run? 3. Okay, so how did you figure that out? Well, you say, where's 0? And you spot it. It's right there. And then you just follow the arrow to the next critical point. Wherever that next critical point is, that's where you drift to. That's it. That's all you have to do. Find where your initial point is, the y value, not the x value, the y value. Find the y value, just follow it along. And whichever critical point you end up at, that's it. And you're done. You can't pass through a critical point. You just go to the next one. If you are asked to plot, basically it's very simple to plot. You just draw your constant solutions, and then you just say, well, what's the behavior? You're going down, or maybe you're going up. So that's essentially the things that can happen. So just constant solutions, and then up or down. All right, that's about all I have to say about autonomous. You're still good. Wow. Okay. All right. That brings us to our favorite type of differential equation, constant coefficient differential equations. And this is good. We like these because there's a beautiful flow that's happening here. And so essentially, the flow is the following. You have a problem, an ordinary differential equation problem. And so constant coefficient just means all these are numbers. There's no functions of x. Life is good. So then you say, hey, that can turn into an algebra problem. And we like algebra. We spend a lot of time on it. Years of our education has been dedicated to algebra. And then you say, hey, since we have an algebra problem, we know how to solve. So we can find the solutions to the algebra. So that's the flow. Whoops. Well, I did not plan that well. That says solutions to algebra. So again, what's happening? We have our differential equation problem. We turn it into an algebra problem, just the same coefficients. The power of r matches the power of the derivative. The solution here, when we talk about solution, we mean the roots. So we solve the algebra problem. And then once we have our solution to our algebra problem, we say, oh, that translates into solutions to our ODE problem. And that's by saying, I know how to turn roots into solutions. So if I have a real root, like 1 or 2, I'll have like e to the 2x if it's 2, or e to the x if it's 1. If it's repeated, I have some extra factors of x I put in at the start. If I have complex roots, I'll have exponential times sine or cosine. And I know that sine and cosine always come in pairs. And so I know how to translate every single root into a function. And so that's the flow. Differential equation problem becomes an algebra problem, which becomes an algebra solution, which becomes a differential equation solution. This, by the way, is not the last time that we're going to see this flow. Now, we might possibly, by the way, have one more step at the end, which is initial conditions. And that's depending on the problem. But that would be, again, if initial conditions were given to us. Okay, well, the next thing is just sort of a philosophy. It's really two ideas here. We'll start with this idea on the left. How do you go about solving a differential equation problem where we have an f of x here. Oops, I missed this. There should be a little f. And it's a couple of steps. It says, hey, first off, replace f of x by 0 and find solution. So in other words, you find the solution to the homogeneous problem. And so we could call this the complementary solution. And if we start off with homogeneous, we're done. Life is good. If we didn't, then we say, okay, then we'll find just a single solution. Just one is enough. One solution, a particular solution to our differential equation problem. And, well, it actually takes a lot of work to find that solution. And we'll talk about the ways to do it here. So what do? Well, the particular solution says, look, my job, handle the f of x. And complementary solution says, great, no problem. My job will be to handle initial conditions. And they're like, yes, our powers combined, we are the solution. So that's why you have both of them. Yp, the particular solution, Yc, the complementary solution. So that these arbitrary constants, are what let you solve for the initial conditions, and the particular solution makes sure that the statement holds. So that's the idea. Now, how do you solve this? Step 2. Well, there's 2 general approaches. So one way to approach it is called the method of undetermined coefficients. Now, this is very precise. It only works, we have to have a nice differential equation, constant coefficients, linear differential equation, and the function on the right-hand side, this function f of x, has to be a nice function. In other words, it has to look like something that we're used to seeing coming out of a constant coefficient linear homogeneous equation. So, how does it work? Well, you solve the homogeneous differential equation, which is what we did. That's the same step 1. We always start with the homogeneous. And then we say, all right, we're going to figure out what our particular solution looks like up to our coefficients. See, the reason we call it undetermined coefficients is we know what our pieces are except for the coefficients. And the way we do it is we say, well, you grab each piece of f of x, and then you just follow a couple of checks. If you have powers of x among your pieces, you have to make sure you have all lower powers of x. If you have sines or cosines, make sure sines and cosines always come in pairs. And then after you finish those first 2 parts, the last thing you say is, all right, is there any overlap with what we found in the homogeneous solution? If there is, we have to bump. So you have to make sure there's no overlap. And then you say, all right, now I have the form. To find the actual coefficients, we plug in. So what we talked about at the very beginning, that like verifying, that's what you're doing. You're plugging your Yp in, setting it up like you were setting up to verify, and say, all right, what would have to be true about my coefficients? And what you get, well, you get a system of equations. You know, you might have like 3 equations, 3 unknowns, 4 equations, 4 unknowns. But you solve. Now that's one way. There's a second way. But before we talk about that, we also should talk about the Wronskian. So the Wronskian is used to test for linear independence. Now, the reason we cared about the Wronskian is essentially it tells us, are these functions distinct from each other? In other words, if I grab a function, is it giving me something new, something I haven't seen before? So that's what we do. And the way it works, it's actually really clean. If I have 2 functions, then the way I set my Wronskian up, it's a 2 by 2 matrix where I take the determinant. So that's what these straight lines mean, determinant. And the first row are my 2 functions. The second row, the derivatives. And so make sure you know how to take your determinants. So going down, going up. So you'd have y1, y2 prime, subtract y1 prime, y2. So know how to take a 2 by 2 determinant. In a similar way, we do the Wronskian of 3 functions. y1, y2, y3, that's the first row, the functions. Second row, derivatives. Third row, second derivatives. Now, you might say, what about if I had 4 functions? Well, that's not our test. We're not going to ask you to do more than 3. We might not even ask you to do 3. So make sure you know how to take determinants of 3 by 3s. It's, there's a couple different ways. There's cofactors, and then of course there's going on diagonals with wraparound. So make sure you know how to take that, because it might be asked. Now, how do we read the Wronskian? Well, the answer is it 0, non-zero? If it's non-zero, we like it. It says these functions really are different from each other. And that means that we get a unique solution. If it is 0, uniqueness breaks down. So sometimes we might say, oh, well, the Wronskian is 0 at, say, 1 and 4, and so that says, great. As long as you avoid 1 and 4, you're good. So maybe if your initial condition is 2, it says you're guaranteed up to 1 and 4 a unique solution. But all bets are off once you hit 1 and 4. That's what happens with the Wronskian. And the reason I want to mention the Wronskian is it shows up in variation of parameters, because our other way of finding a particular solution. Now this one is a little bit more narrow in some sense in that we can only do second order. Well, we only talked about the formula for second order. There are formulas for any order, but they get more interesting. So we're not going to do those. And so we have a second order differential equation, but it doesn't have to be pretty. We can have functions of x, for instance. So we have our homogeneous solution, so y1 and y2, and we're trying to find a particular solution. So see how we have 0, that means they're homogeneous solutions. Here, f of x, particular solution. The way it works is we say, our solution looks like a combination of y1 and y2, where we add on some functions u1, u2, which are unknown. Well, it turns out that in order for this to work, that leads us to 2 equations, 2 unknowns, which we can solve. And, well, we can solve for u1 prime and u2 prime. We integrate, and we get our formula. You don't have to memorize the process. You don't have to even memorize the formula. The formula will be on the equation sheet. But you do know how to have to use it. And that is actually my last page. I don't have anything else. I will say, for those of you getting nervous, there's a lot on here we talked about today. Will we test you on absolutely everything? No. We don't have enough questions. There's only 6 questions. But we do get a final. So if we don't test you on it now, we can test you on it later.